Having looked now at unknown sample Q, presuming you, of course, have looked at unknown sample A, where I went through a lot more detail on all of these tests and ideas. So starting off with our unsaturation test, we can see there is a negative result for that. So it's a negative result for the two tests. So no double bonds, no alkenes or alkynes. Note that double bonds, I am referring to carbon double bonds, not, for example, a carbonyl. So the BR2 test just says don't have an alkene and you don't have an alkyne. We have a positive oxidation test. So likely to have, an alcohol or an aldehyde. So one of these is potentially present as they are able to be oxidized under those conditions. And we have a negative carboxylic acid test. So there is no carboxylic acid. That one's pretty easy. From the IR, what can I see? Firstly, I'm going to ignore anything under 1500, the fingerprint region, at which point I have two signals worthy of consideration. And then I have the lack of something that is also worth noting. Let's pull these apart. So my signal at about 1700 is likely the result of a carbonyl. So I have that carbon double bond oxygen somewhere in the system. At this point, I don't know if it's a ketone or an aldehyde. I'm not sure. I might have thought it could be an ester or a carboxylic acid. I know it's not a carboxylic acid as that's come out from the wet test. We could consider an ester and we'll come back to that soon. We do have our signals at about 2900, which again is typical for our carbon hydrogens. What's interesting to note is a lack of anything at that higher region at about 3300, which means that there's unlikely to be an alcohol. And we already knew there was no carboxylic acid, so it doesn't really help us there. But it does help us narrow down that, well, I thought I had an alcohol or an aldehyde. At this point, I'm like, oh, I'm more likely to have an aldehyde in the system. It's worth noting that I said maybe the ester could be there for that carbonyl, but I had the positive oxidation test. Esters can't be oxidized under those conditions. So unlikely to be an ester either. We're really likely looking at an aldehyde at this stage. Looking at my molecular mass, I know I have a molecular mass of 86. I'm very glad that that was written to the left because good luck seeing in there. And this is a good example that a mass spectrum can, depending on how it is collected, can be very unstable. So our molecular ions may not actually survive. So we've been told in this case that the mass to charge ratio is 86. Other than that, I'm not going to pull out much from this mass spectrum. It's not particularly useful. I can't even really look at those molecular ion peaks and say, oh, there's no chlorine or there's no bromine. I can't really see them. So all I'm going to say is that its molecular mass is 86. So at this stage, I don't have a lot to work with. I know 86 is a bit heavier, and I know that there's probably an aldehyde in the system. Okay, it's a step forward, but not much. So we're going to go into our NMR data to really pull out what I'm looking at here. Firstly, I look at the carbon environments, I can see there's 5. At which point I'm immediately thinking, well, how can I have 5 carbons in a non-symmetrical system so that I can see all 5 of them? And the most obvious way is to consider a pentyl group. If I move any of those carbons around, I will induce symmetry in the system, so I won't get 5 of them. So this is at least a good, really first guess of the way that those carbons could be arranged. Note that I can also see a signal at about 200. 200 ppm, and that's likely a carbonyl, specifically a ketone or an aldehyde. Carboxylic acids and esters come up a little lower, about 150, 160. So we're likely looking at that aldehyde peak that we predicted earlier. And because it's an aldehyde, it has to go on the end of the molecule. So before I even go into the proton NMR, I have a pretty good guess at the structure that I'm looking at. I have all 5 carbons, no symmetry. I have my aldehyde. And if I went and looked at the molecular mass of this particular system, I'd find it was about, oh, I don't know, 86 from the value before. The other 4 carbons, worth noting, are between 0 and 40. For some reason I keep switching the R and the O. So they're aliphatic, meaning that they're not near anything particularly electronegative. They're more in a alkane-like region, which again, looking at the molecule I've drawn, makes sense that those 4 carbons are likely these 4 on the end of this chain. I'm going to go into the proton NMR. Now, again, I've got a pretty good guess of what this is, but let's be sure of it. Starting off with chemical shift in the high 9s. So I have, I should point out that I have 5 environments. Again, makes sense. There's no symmetry in the molecule that I've been drawing. I have a triplet at about 9.8, which is an aldehyde proton. Those are the only ones that come up that high. And neighboring SCH2. Again, we're trying to explain why there's a triplet in this case. So I have the number of peaks being 3. That means that I have 2 neighbors, and I'm getting that from the CH2. I have my peak area ratio of 1, which makes sense, as I am currently talking about and looking at this aldehyde proton. After that, there's a lot to unpack in terms of the number of coupling environments, but very quickly, we're going to use this to confirm the chain that I've drawn above. I would expect the next environment down to be these 2 protons, which means that they have 3 neighbors in total. So I would expect a quartet, and I would expect an integration of 2. If I have a look, the next signal down is indeed a quartet, and we're told it has an integration of 2. Continuing down my chain, as I'm getting further and further away from my aldehyde. So looking from the perspective of these hydrogens, there are 4 adjacent to that. So there are 2 hydrogens here and 2 hydrogens here. So I'd expect a pentet. And again, I'd expect an integration of 2, which is what I'm seeing. Continuing down, I'm just going to keep proving that table. So really what I would say is rest of spectrum consistent with CH2, well, maybe I'll change this to straight chained pentyl system. Let's go with molecule. So it's all very consistent. If I follow it all the way down, I could say, yes, this is a pentyl chain. So I knew that it was an aldehyde. I knew there were 5 carbon environments. Best result is pentanal. So you might note that I cheated a little bit in this one. I collapsed it all down rather than talking about every single signal and just saying, well, look, if I look at a couple of them, yes, this is consistent with that chain overall. So that is our unknown sample Q and how I would explain that one.